Hey guys, I'm back with another video. Today I'm going to be covering specific gravity. This is a concept in AP Physics 2, specifically in Unit 1, which is fluids. And so I'm going to be covering that here today. Let me get my marker ready. Alright, so, what a specific gravity is it's a very simple concept. I'm going to try to keep this video pretty short. So, what it is really, so usually it's demarcated with uppercase S, and there's an equation for it. It's pretty simple. Sorry about that, that's supposed to be a line. And so what it is, you take the density of an object, which by the way is not D. Maybe some of the younger viewers here or someone who's not used to it. It's actually marcated by the Greek letter rho, which looks like the letter P. And so that's what is commonly used for density. That's how we know density. And so the specific gravity can tell you a few things. And I'll get into those in just a bit. So what it is basically you can take the density of an object. I'll put that as PO, not P naught, but PO, O for object. Then I'll do this as P fluid. And for now, let's imagine that this fluid is water. So what is the rho? Rho is the letter, the Greek letter used right here. That looks like a P. It's actually called rho. And so let's say it's water. Okay. So let's say it's water. Then what we're going to have, and so what it is 1,000 kilograms per meter cubed. And some of you might be confused. You may have thought it was 1, but actually the units were different. So some of you, I remember when I was younger, I learned the density of water is 1. Now the units weren't as clear back then. But it turns out that the units that we used back then when I was a kid, we used, it was grams per centimeter cubed, or grams per milliliter. So that's what we used back in, I think, middle school. And so, but in Physics 2, you more commonly use this type right here. You use kilograms and meters as compared to centimeters. You do use centimeters and grams, but they're much less used, and they're typically expect you to convert them to kilograms or meters cubed for the sixth instance. So it's 1,000. This is the density of water. Sorry about, I'm still getting used to drawing straight lines. So, and just for some good measure, specific gravity is unitless. Specific gravity doesn't have a number associated with it. It's just a number. So specific gravity, what it can tell you is, I'm going to write this on the side. So if S, which is specific gravity, and let's say, actually let me write this down first. So if S, or specific gravity, is greater than 1, the object will sink. And so if it's greater than 1, then it'll sink. If it's less than 1, so if we have the specific gravity being less than 1, then it will float. And I'll tell you something. I'm actually gonna put this in. I'm gonna put some rainbow ink around it because I'm gonna come back to this. Okay. And if S equals 1, then that means it has the same density as the fluid that it's in. For our example, we're gonna have water in here, and so that means if something that we put in water has the specific gravity of 1, that means it has the same density as the fluid, and it won't really float, but it won't really sink either. It'll kind of be, if I remember correctly, correct me if I'm wrong, it'll kind of just be in the water. It won't be at the bottom, but it won't be up here, if you can follow my cursor. Like, it'll be kind of in the middle, like, so yeah, it won't really go to the bottom and sink, but it won't really be up here to float. And I said I'll come back to this, and so let's say our object is Mercury, and what is the rho or density of Mercury? Oh, no, that's more like a P. Yeah, there we go. So what is a rho of Mercury? And Mercury, as it turns out, actually has a pretty high rho, much higher than water. So 13,900 is actually the value. It is, again, kilograms per meter cubed. Alright, kilograms per meter cubed. So that is the density of Mercury. And I'll put PM. Okay, and so based on this, if we put PM, let's say we have some mercury, and we put it in water. So if we use our equation for specific gravity, we'll get 13,900 over 1,000, and that's going to be the specific gravity of mercury in water. And so that obviously, if you divide this 13 point, so it'll amount to 13.9 as the specific gravity. And by the way, this is actually an estimate, it's not exact. And usually in physics 2, or actually in any physics class, you won't really need the exact value. Maybe in higher level physics, but in high school physics, it's not as necessary. So these are actually just estimates, but estimates are good enough. So, okay, so right here, so if S is equal to 13.9, we can go right here and check, and I forgot to write, this is sink. So if S is greater than 1, or specific gravity, then the object will sink in this fluid. It will float in this fluid, and if it's exactly the same, then it'll kind of stay in it. Stay in. Comma. Alright, so the S here is 13.9. If you divide rho here, rho of mercury, we'll put that in place of rho object. And we put water in place of rho fluid, then we would get 13,900 over 1,000, which is 13.9. And as I said before, specific gravity doesn't have any units, because the units for these cancel out. So specific gravity is 13.9, and when it's 13.9, we can just put it in here, and we'll put this in this test, and we can see that it sinks, because 13.9 is greater than 1. So that means if you put in mercury in water, it'll sink to the bottom. Now, what if we were to do this the other way around? What if the object was water, and what if mercury was the fluid? Because you can have liquid mercury, and water is a liquid, and then you put that in, and the object can be liquid, by the way, I forgot to mention that. It doesn't have to be a solid, it can be a gas, I'm pretty sure, as well. So if you put that in, you have 1,000 over 13,900, which is, if you do the math, it's 1 over 13.9, and that obviously, 1 over 13.9, yes, 1 over 13.9, or 10 over 139, which are both, they're both equal, and they're both less than 1. That means that this object will float in water. And so I drew this red box here to kind of represent, like, let's say this was the Mercury that we were talking about. It would sink. But what if it were to float? Now, one cool thing you could do with specific gravity, and this is where I'm coming back to this little rainbow outline that I made. Let me erase the stuff about the Mercury. We're going to use a different material. Alright. Alright. So, I'm going to erase this box too. Alright. So, let's say we were to use something like ice, and I'm going to do rho, sorry, even I get confused, rho of I. So that means, this is about, you search it up, it's around 920 or 930 kilograms per meter cubed. Trying to write a bit faster. I said I'd put this a bit short, and it's going pretty long. And it's about 920. It can sometimes be rounded to 930. It's around 920, 30-ish. The exact value isn't too important, but either way. So here we go, and we can put this in, and let's say we have an object, and this red box here is ice. Let's just say it's ice. And then so we put that into the equation. So the object is ice, the fluid is water, which doesn't change in density, so it's 920 over 1000. So based on this, we can say that the ice will float because S is less than 1. The S specifically will actually be 9.92. That'll be your specific gravity. Again, no units. And then once that's in there, once you've gotten that, then what you can do, you can actually determine something pretty cool. When S is less than 1, the specific gravity that you get is actually the proportion of the object that stays under the water. So if you put a block of ice in, let's put this in a much bigger and more relatable scale. Not too relatable, actually. Let's say you might have heard the term that 92% of the iceberg is actually under the water, and that's true. And it's actually due to this concept of specific gravity. Ice, which is what an iceberg's made out of, is 92% under ocean water. And ocean water, it has a slightly higher density because of the salt content, but generally it's about the same, 92%. And this is actually the scientific backing behind it, because the specific gravity is 92% of it. And so with this, you can actually determine how much, so let's say I drop an ice cube. 92% of that ice cube is going to be, below the surface of the water. The rest of the 8% is going to be above the water. So you can determine this not just for ice, but for any object. Let's say a block of wood has 750 kilograms per meter cubed in its density. So if you find the specific gravity of that in water, we're going with water because it's a pretty simple measurement. If you find the specific gravity of that, then it'll be 750 over 1000, which is 0.75, meaning that if you put that block of wood in the water, 25% of it will still be above the surface, 75% will be below the surface. So that's a pretty interesting concept. I hope you enjoyed the video. Thank you for watching, and if you could please hit the subscribe button, that would be very good. That's it for this specific gravity video. I hope it was helpful. And yes, that's about it. Thank you for watching. Be sure to subscribe.